So in lesson 6 here, it says we're going to describe velocity today and displacement quantitatively. So we're going to use displacement today. Again, define, compare, and contrast scalar and vector quantities. And we're going to look at basically one dimension, don't worry about that, but scalar motion and work done on an object or a system. And we're going to use some algebra and graphing techniques for that. Okay, so today, first things first here, we're going to talk a little bit about what velocity is. Okay, and sorry, I'm just going to bring up the notes here in a quick sec here just to make sure I'm not skipping anything on you guys here. Let's see. Oops. 1 second here, I'm almost there. Okay. So like I said, today we're going to talk about velocity. And velocity is a vector quantity. It's the vector equivalent of speed. Okay? It's the vector equivalent of speed. So you're going to have to write that in there, of course. Okay? To calculate velocity, use displacement and time instead. So here's the formula. Okay? Here's the formula here. And you might notice that this formula looks very, very similar to one we've already talked about. We've talked about speed so far, yes? Well, this is the formula for velocity. And the difference between these, of course, I'm just going to label this here, velocity. And if you guys want, of course, we know that, hopefully we know that this, of course, is the velocity here, actually. Okay, this is the time, and this is the displacement. Okay, displacement. So, this is going to be similar, yet a little different than speed. The speed formula looks like this. Okay, and of course, we talked about distance. And this here was speed. Okay, and t, of course, is time. Yes. So very similar, but you're going to see that we have some, in fact, vectors here. Okay. So we are going to talk about vectors instead of just scalar quantities for velocity. Okay. Now it's really important to keep these two straight, of course. Formulas are very similar, yet we're going to get different answers at times as well. Sometimes we will get the same answers, sometimes we will get different answers. Most of the time we get different answers, okay, just so you know. Okay, and I'll show you some examples coming up here. All right, oopsies. So here's example 1, okay. A person walks 10 meters east away from a bus stop, realizes they went the wrong way, turns around and walks 25 meters west, and they do this in 20 seconds. What is the average velocity of the person? So first things first, I'm going to label some variables here. Okay, that's velocity. That's what I'm looking for. There's my delta t. That's my time. Okay, this is one vector, and this is my other vector here. Okay, and I don't have enough room there, but that's 25 meters there, of course, and you guys can see that on your questions there. Okay. So it says, what's the average velocity? I'm going to start with the velocity formula, which is displacement over time. Okay? And again, I'm trying to solve for this right here, so it looks like I'm all set up. I'm good to go there. So delta V here is going to be the displacement over the time, which is 20 seconds. Time is 20 seconds. Okay? Now, what's the displacement for this scenario? Okay, what is the displacement? So again, we might want to talk a little bit about assigning one direction positive, assigning one direction, obviously the opposite direction would be negative. We could do that. Okay, we could draw a little diagram for ourselves as well. And again, always remember that we have in this section here north, this is west, east, and south. I don't know if you guys know this, little tidbit of information for you. You can chalk this up to a little bit of extracurricular learning here. Do you know what if you actually do you know what NEWS news spells news, eh? Look at that. News. That's where it kind of came from. Well, that's where news came from. Anyway. Interesting. So we're going to go 10 meters east. Okay. So I start here, and I go 10 meters in the east direction. I turn around. It says, "Oh, realize I went the wrong way," and walks 25 meters. 25 meters west. Okay. What is the displacement of this scenario? Somebody could answer me, please. Anyone, please, quickly. 15. Okay, 15. So it's like I started here, and I actually went to here, right? So that would be what? 15 meters. Let's not forget, though, displacement. We need a direction as well. So that would be in the west direction, yes? Okay. So went 10 meters east, turned around, went 25. Where did I start? I started here. Where did I end up? I ended up here, yes? So that section right there, that's my 15 meters in the west direction. Is everyone okay with that? Yes or no? Give me a yes or no, people. Somebody. Anyone? Yes. Thank you. All right. So that's our actual displacement. Okay. So that's what's going to go here. Now notice, what is it? It's actually 15.0 meters in the west direction. Okay. And of course, look, this is a vector. Velocity is a vector. It includes an amount and a direction, yes? So when we divide these two numbers, you're going to see something a little different today. So 15 divided by 20, of course, is 0.75. We need what? I think we need what? 3 significant digits, maybe? Yeah, I think we need 3, right? So I'm actually going to go 0.750 meters per second. And that's going to be in the west direction. So notice, okay, that, of course, we have a direction with this as well as a magnitude. Okay, so we need to include the direction as well today. This is velocity now. With speed, we don't have to include the direction. And in fact, we get an entirely different answer for this question. And that's going to be some of the questions coming up here. What's the speed? What's the velocity? Okay, they're not always the same. In fact, they're rarely the same. They could be the same. Okay. Another option here, if you remember from last day, you could say, okay, if you're not sure about this vector thing here, you could say, let west be positive. So if you're looking for delta D here, you'd say what? 10 meters east. I'm just going to do the shorthand here. And 25 meters west. Okay. The west is the positive direction, so this is a negative 10 meters. This is my positive 25 meters. And if I add those two together, I get a positive 15 meters. And the positive, remember, since west is positive, I'd say that's a 15 meters in the west direction because it's a positive. Okay. And again, that's how you get that there, perhaps. Okay, so if you want to do that, you most certainly can as well. Okay, any questions on that first one there, anyone? Again, we have to remember that velocity is a vector. Okay, so we need not only this, I don't want to say speed, but not only the magnitude, but also a direction. Which way is he headed in? Okay. Basically, if you look at this question here, okay, if he starts here and he actually did this and this, obviously his speed would have to be, that'd be a total of 35 meters, right? And his speed would have to be quite high to do that. If he went at, if he went 35 meters in 20 seconds, that person's going to have to travel quite quickly. okay? If another person started here and just went to here, he could go a lot slower. In fact, he could go 0.750 meters per second in the west direction. Okay, is there any questions, anyone? Speak up. Okay, example 2. Well, it says here a boat travels with a velocity. So right away I think, okay, there's my V right there. And notice it's got a direction for 14 seconds. That's my time. What's the displacement of the boat? So this is a kind of a similar kind of question to the speed ones we looked at before, and that's why we kind of started with that, because there's not a whole lot of difference between these two formulas as far as solving for variables, et cetera, et cetera. However, okay, we do have to understand that there's a velocity, in fact, here and a time. How do I get displacement by itself? So how do I solve for delta D here, basically? Displacement. Well, I'm going to take this and times it by T, and I'm going to take this side and times it by T, and that's going to get rid of that. Okay? And it looks like, in fact, we have displacement by itself. So delta D is the time times the velocity. Okay, is how I find the displacement. And don't forget the little arrow above, because if you don't put the little arrow above it, okay, then technically you're talking about distance. So it means something different. Okay, so the time here is what I say, 14 seconds. The velocity is what, 8 meters per second. And notice it has a direction with it. Okay, and you're going to notice that we're going to need that direction. Okay, because remember, displacement includes a direction. Well, what's 14 times 8 here? 14 times 8 is what, 112. Okay, 4 significant digits, 3 significant digits, so I probably need to have 3 in my answer. The seconds will cancel with the seconds, and I'm going to be left with meters and north. Okay, vector, vector, yes, and that would be my answer for that one there. Okay, any questions on that, anyone? Yes or no? Questions? If you guys need me to slow down a little bit for you guys to copy some of this stuff down, let me know, obviously, because I don't know, I can't see you, obviously, so like I can in the classroom, so I don't know where you guys are at or whatever kind of thing, so speak up. Okay. All right. Next. So here is, sorry, I guess I'm going to fix this a little bit here, but here's example 3, and there's the answer. So I want you to actually go ahead and start solving this, okay, for me, please. And we're going to take a little break here, and I'll let you guys take a look at what you need here, okay? This should be 10 to the 2 here, so that's 10 to the 2 power, and this is 10 to the 2 power as well. So times 100 basically for those two. And yeah, okay. Now, and this right here should be times 10 to the negative 1 hours, and this is 10 to the 1 minutes. Go ahead and start solving that, please. Okay, an airplane's flying at a velocity. I would probably, obviously, there's your velocity right there. Don't forget there should be a direction here, which there is. It's just right here, that's all. But there's your direction. And you'll notice that this also, okay, travels that many kilometers west. How long will the plane be flying? So you're looking for delta T here, of course, and that would be your delta D, okay? And you'll notice, how do I know it's delta D and not just distance? Well, because they include a direction, okay? So directions and directions, we need to use both of those because there are vectors, okay? So I'm going to give you a few seconds there. Go ahead and do that. All right. So we were looking for the time. How long will it take? So again, okay, I want to see all the work for this. You know, when we start this question here, I expect to kind of see Okay, how are we going to get delta t by itself? This is important. Okay, we need to be able to isolate variables. Again, if you're not sure, you can always ask for extra help here. We're going to multiply both sides by delta t to start with here. So that's going to cancel that, and delta t here as well. Okay, I then am going to have this delta t times v, like so, vector delta d. Now, if I want to get the time by itself, because I want to solve for time, I need to divide by v and divide by v, and that'll cancel that. Okay, so really what we need to have here is delta t should be the displacement over the velocity. Okay, like so. And the displacement we said was what? 400 kilometers, basically. If I don't know if it's okay with you guys, but well, you know what? I'll just type that in here. 400 kilometers west. Okay, 400 basically, and it's traveling at 900 kilometers per, what is it? Per hour, I guess, right? Per hour in the west direction. Okay. And again, you'll notice that time, does time need to have a direction with it? Does time have directions? No. Okay. But you'll notice, conveniently enough, that kilometers is going to cancel with kilometers. West is going to cancel with west. What are you left with? You're left with, of course, hours here. Okay. So 400. Now you got to type this in properly. If you're going to do this, you're going to have to either use brackets here, or you're going to have to use the e function. Or if you just go 400 divided by 900, you get 4/9, which is 0.4 repeating. So 0.44, how many significant digits? I think 3. 0.444 hours would be acceptable in this case here. Yeah, 3 significant digits. So that's an option. Okay. Now I know in the answers they say 4.44 times 10 to the negative 1 hours. That's the same thing. That's okay. You can just leave it as 0.444. That's fine too. Okay. Now, for some reason, they also put it into minutes here, and I'd say I wouldn't bother unless the question asks. But if it does ask, how many minutes is this? Well, then I guess we need to convert it to minutes. Okay. Now, this question I don't think says that. However, if we did want to get it into minutes for a little practice here, 1 hour is 60 minutes, right? So the hour and the hour will cancel. And if I take 60 times 0.4 repeating, and again, you should not round, of course, you get 26.6 repeating minutes, okay? Or 26.7, I guess, all said and done rounded, okay? And again, I don't think you really need to put that in scientific notation. I think that's fine like it is. But again, if you want to, I guess, it would be what? 2.67 times 10 to the 1 minutes. Okay, but 26.7 minutes makes a lot more sense to me, or 0.444 hours is perfectly fine, okay, for that question there. Okay? Any questions, anyone? Say yes or no, please, somebody. Yes, no? Questions, anyone? Okay. Now, we're going to get to example 4 here. And example 4, okay, I think this is our last one, isn't it? I think, roughly. It is quite the process here, okay? It says, first of all, a car is driving west at 65 kilometers an hour for 2 hours. Now, before turning around and driving east at 75 kilometers for 3 hours. What is the average velocity? So we're looking for, obviously, v, vector v. Vector v, it sounds like cereal, doesn't it? Vector of the entire trip. Now, if we're looking for the velocity of the entire trip, okay, what we need to do in this case here is a multi-step kind of problem here. Now you'll notice, okay, even with this, there's west. This is a velocity, I guess, and this is a time, okay? Now, this is a velocity, and this is a time as well. Okay, maybe I should put things there. Okay. So it says here, what's the average velocity of this trip? Well, we got, unfortunately, what's the average velocity? It's not just as simple as saying, well, look, I'm going to take 65 kilometers and average it with 75. It's not that simple because, look, the fact is, if we just average that, that's 70 kilometers an hour. That's obviously pretty easy. But remember, we also have two different directions we're going. And if we're talking about velocity, that is the displacement over the time. Okay? Even if you were to do the distance over the time, it probably wouldn't be 70. Because not only that, you also have different time frames here. One's going for 2 hours and one's going for 3 hours. Okay? So remember, you're going faster for 3 hours than you are for 65 for 2 hours. So that's not going to average out exactly either. Okay? So even if you were talking about speed, distance over time, that's probably not going to work out either. Okay? Because again, you know, this is going to count for more than the 2 hours will in this case. So we have to remember when they say what is the velocity means we need the displacement over the time. Okay? Well, you know what? I can do this. I don't know about you guys, but that's 5 hours. Okay? I know that. Okay? Because it's 3 hours one way and 2 hours another way. So that is the total time it takes. Okay? That is the total entire time that it takes. However, what is the displacement? Well, if you look at this question, I don't know about you, but I don't see delta D up there. I don't see the displacement anywhere there in this question. This is, like I said, velocity. So is this. This is also velocity, and I got some times here as well. So I don't even know what one of the displacements is, let alone both of them. So I'm going to have to do an extra calculation here. I'm going to drive west 65 kilometers for 2 hours. So I'm going to just draw this out here. Now, I don't know exactly where I'm going to end up or anything like that, but again, if I'm going to go west 65 kilometers an hour for 2 hours, okay, then I'm going to what? Drive east. So I'm going to go east. Now, I assume this is going to be a little bit longer here because it's obviously 75 kilometers an hour for, 3 hours, okay? And remember, what we're looking for is basically this, right? We're looking for this section here. That's the displacement, okay? Well, how am I going to find the displacement? Well, we know that the velocity is equal to the displacement over the time. And again, if I'm looking for displacement, I want to rearrange the formula to say, okay, how do I get displacement? I take the velocity times delta t here, boom, boom, delta t, okay? So if I want the displacement, I'm going to take the time, which is, I'm going to do the top one here first, 2 hours, and I'm going to multiply it by the speed, which is 65 kilometers an hour for in the, what is it, I said west direction, okay? I know that's kind of, sorry, I'm kind of cutting it off there. And 65 kilometers an hour times 2 is 130 kilometers in the west direction, okay? So if I went back to this part right here, that blue line right there, that blue line would actually look like this, 130 kilometers in the west direction, okay? Then I need to turn around and I need to figure out this green line here. So now I'm going to say, okay, I'm going to turn around, I'm going to go this way for a certain amount of time, and I'm going to do the exact same thing. Delta D for this green line here is equal to the delta t time times the speed, right? So the time for this green line here, which is this one right here, is 3 hours at 75 kilometers an hour. So 3 hours at 75 kilometers an hour, and that's in the east direction. Okay? If I multiply those together, I believe it is 225. Is that right? Yeah, 225 kilometers in the east direction. Okay? So now, okay, I want to find out, again, remember, I want to find out this red section there, that question mark part, right? And to find that out, I now have two displacements, okay? I got my blue one here, which is going west, and I got my green one here, which is going east, okay? And by the way, that was 225 kilometers in the east direction, okay? Again, we can let the east one be positive and the west one be negative, basically, and I can, add, subtract those two. Whatever you want to do there. It should be what? 225 and 130. 95 kilometers in the east direction would be this part right here. 95 kilometers. It just froze on me. That's nice. In the east direction. I was wondering when that was going to happen. Okay, bear with me. So again, we have this red vector here, okay, that was 95 kilometers in the east direction, okay? And like I said, when I come over to here, my displacement, and we already talked about how the time is, 5 hours basically, and 95 kilometers in the east direction, okay? And when I divide those two, I think that gives me 19, I think, isn't it? 19 kilometers an hour in the east direction. And don't forget, we need to have a direction with that, of course, because it is, a vector. Yes? Okay. Good. Is there any questions on that, anyone? And again, this should be times 10 to the 1 here. Okay. Now, as far as significant digits, they weren't very specific here. It's 2 hours and 3 hours. So maybe we should only have one significant digit, but just a reminder that sometimes we'll try and be a little bit more specific with that. Either one of those would be probably okay in this example here. Time, remember, sometimes is, even if it's just one, doesn't usually count sometimes because it's a kind of an infinity kind of thing here. So, but either one of those would be acceptable in this case here. If I was going to do this question for a quiz or a test, I'd probably put 5.0 kind of thing. So according to the previous examples, just to kind of keep it consistent for you guys, so you're not really guessing as to what you need to do there, okay? So like for the 2 hours and the 3, I'd probably put 2.0 and 3.0, okay? Any questions there, anyone? Questions? Yes, no? Okay. So quite a lot of, quite a lot there to deal with due to that, unfortunately. And like I said, sorry that my board froze there, but whatever. Okay. All right. Well, let's see here. I think we have time. We can probably talk about. Oh, don't tell me this is frozen too now. All right. So in this lesson, in the rest of this, it says here, let's use graphs to analyze the average velocity and a position versus time graph. So again, you'll notice this is very similar to what we looked at for our very first graph. Our very first graph was what? Distance versus time, speed. And in this case, we're going to talk about position or displacement versus time, okay? So a few things that you need to fill in here. The manipulated variable is time, okay? And it is plotted on the x-axis. Okay. The responding variable is position, or d, displacement, and it's plotted on the y-axis. All right. So let's take a look here, and that's what we should have for that one. Okay. Is everyone good with that so far? Okay. And there's a little space there, and it says the slope of position versus time graph is equal to what? So the slope in this case, well, remember, let's just go back to here. This, by the way, was called the speed graph here, yes. We had distance and time, and this, of course, gave me what? Average speed, yes. So what do you think the slope gives you in a displacement? Okay, and let's maybe copy down both of these here, and this here, delta t here. This would, of course, give me what? This is the average velocity. That's what the slope is equal to here. Okay? And you can kind of see that right here. They give you kind of the formulas that you want to talk about there in that regard there. Okay? So that would give you the velocity there, the average velocity. Okay? Again, we're talking about the change in displacement over the change in time. Okay? Is that good? I'll give you a few seconds to copy that there, and then we'll. All right. Are we good there? Yes? No? Not quite yet? Okay. All right. So, again, very similar to the last one that we talked a little bit about. And here we go. Okay. So we need to draw a slope versus time graph. Or, sorry, slope. A displacement versus time graph. And here's our numbers here, basically. And we got some information that goes with this. So what I want you to do right now is, obviously, as you guys can see there, you guys have the same information as on your sheet there. Let's go ahead and let's plot, and let's make a graph of this. We want titles. We want labeled axes, okay? And don't forget, with the labeled axes, we also want to include, of course, direction, because we're talking about displacement here. So let's go ahead and figure out a scale for us. Let's figure out, and let's start plotting some points here. And I think these points are going to work out pretty nicely for you here. So go ahead and start doing that, and I'm going to take a break here, and you guys go ahead and do that for me right now, please. All right. So we got this list of data here, okay? How many squares are on your graph paper there, on your notes there? Somebody? Come on, quickly. How many squares are on your piece of paper there? Thank you. So you got 14 squares, and by the way, it's the same for the x and the y-axis. So you got 14 squares, and again, what we're going to do here is we're going to take the range of the data, okay? So from 10 to 0, basically, so 10, and divided by 14, okay? Now, 10 divided by 14 gives me what? Let's see here. 10 divided by 14 is what? 5/7. So 10 divided by 14. Yeah, about 0.714. Okay, so each square would be about 0.714. Now that's a ridiculous number to use. Okay, in that case there, because again, we kind of want to keep it nice and neat. None of these values would be on the squares then, of course. So we're probably going to round this up to what? So we kind of round it up to the next whole number kind of thing, or something that would make sense for us at least. And I would think that every square probably could be what? 1, I guess. Okay? If every square is 1, we should be okay. We're going to have some squares left over at the end. Not a big deal. Okay? So if we had our piece of graph paper here, okay, this would be 1, 2, every square would be 1, okay? And we're going to go all the way up to 10 here, and we're going to have a few left over, and that's fine, okay? No biggie. Same thing here. So now we have to be a little careful here, because with our range of data here, it's not 100 minus 0. We have to get up to 150, okay? And we're going to divide that by 14, because we have 14 squares. So let's take a look. 150 divided by 14. Each one is 10.71, 714 actually again. And I would say, well, you know what? Again, we're not going to make each one 10. That's ridiculous. So what could we do instead? I guess we could make every one what? We could round this up to 11. Okay? But again, if we rounded it up to 11, you know, could you? Absolutely, you could. Okay, you could. But if you look at any of these numbers, they're not divisible by 11. Okay, so that's probably not going to help me a ton. If you look at most of those numbers, what's a number that would probably go into those? Probably like, you know, for the most part, I would say what goes into all those numbers evenly? Well, I would, you know, you might want to say 10 because this 50 goes into 10, this goes into 10, this one doesn't, okay? So that's not going to work. And, you know, again, we want it to be more than 11, of course, but so 10 is not a great number, but 5 would be an okay number, okay? 5 goes into all those, okay? Now again, we have 14 squares to use. We're not going to probably end up using all of them. That's okay. What would be a good number to use? I would say, you know, 15 might be a good number to use. Okay. If you went, like I said, probably 15 for every square, that would be okay. Is there another number that would be probably just as good? What about 25? Does 25 go into all those? I think it does, eh? Now 25 goes into all those. So let me think about this for a second. If it's 11, okay, so each square needs to be at least 11. Well, that means that 2 squares would have to be what? 22 at least, right? But what if we made every second square 25 instead? Every second square, round it up a little bit to 25. Every second square. Which basically means that every square would be 12 and a half. Does that make sense, everybody? So that's 12 and a half. That would be 25. 12 and a half, that would be 50. 12 and a half, this would be 75. 12 and a half, that's 100. 12 and a half, that's 125. Is that going to work for us? If every square was 12 and a half, what's 12 and a half times 14 squares? Oh, well, that's only, that's right, 175. And we have to get to 150, so perfect. We're going to have a couple squares left over on top, but I think if we do every second square with 25, that's going to work out pretty darn nice. Okay? Does anybody have any questions on that? How I came up with those numbers? Ask. Now, do you have to use 25? Every second square is 25? No. But you just got to make sure that when you get to the top here, that you have enough room, okay, to make sure you can plot all the points, obviously. Like if this was the top of my graph actually here, well, that's not going to be good because I'm going to run out of space. But luckily for us, like I said, you know, what's the next one here? So that would be 12 and a half, so this would be 150. 12 and a half, this is 175. Okay, and I think that's actually where you'd end up there. So I'm missing out on these 2 squares, but basically my graph is going to take up most of that, and I'm going to be missing, yeah, I guess most of that. So that's kind of where we are, okay? Again, we want a title, so make sure you put a title here. We want this to represent our data here, so what is it? Position of a car, so that'd be good thing for your title there. And this is what? Delta D in meters east, yes? And we want to put that in brackets, like so. Okay, we're labeling the side. And on the bottom here, of course, we're going to have the time, as always, in seconds, I believe, yes? Yeah, okay. So go ahead and plot those points there, okay? And do that. And then, I guess, I don't know, do we want to keep going here today? No answers, good answers, I guess. Okay. I think let's plot the points. Now, you're going to have, you notice here that it's got 2 different slopes, okay? 2 different slopes. So I want you to go ahead and calculate those 2 different slopes as well, okay? and we'll talk about those maybe tomorrow. Please note it also says right here, the straight line indicates that there is uniform motion or constant velocity. Okay? Yeah. You know what, I think we'll stop there for today. So I want you to go ahead and plot those points, please. Make sure you do that. Okay? So make sure you plot the points. And we are going to start looking at some questions here. So, let's see. Give me 1 second here, and I'm going to give you some questions to do. I don't think we need to record.